Good morning everybody. Today we will discuss about heat transfer from an annular fin. Now we have shown a typical example of an annular fin. Usually arrangement is such that a hot liquid or hot gas flows through the tube and the tube gets heated, and this tube has to be cooled, or this thermal energy has to be taken away by the surrounding fluid. And that is why this extended surface, which is in the form of an annular fin, has been attached. Now in actual arrangement, this tube may be quite long and there may be number of such annular fins mounted on the tube. But for the analysis, we will take up only one such annular fin surrounding the heated tube. So the annular surface starts from R equal to Ri, where the temperature is T0. In fin terminology, this is the base temperature. And then annular fin is having a dimension, finite dimension, which extends to R equal to R0. And the thickness of the fin is T. T infinity is the temperature of the local ambience. So basically from the base T0, thermal energy will be transferred to the annular fin, and from the annular fin, since the area is getting enhanced, or effective area of heat exchange is being enhanced. So through that area, thermal energy will be transferred to T infinity, which is at a lower temperature than T0. Now, cross-sectional area at any radius is given by twice pi r into T. Therefore, dA by dr is twice pi T. And dA by dr, dA by AR is given by 1 by R. Similarly, up to radius R, any radius R, the surface area is twice pi r square minus ri square. And ds dr is then 4 pi r. So ds dr by ar is 2 by T. So these are the parameters we will be needing: dA dr by AR, ds dr by AR. So again, having the fin in our mind, Ri is the tube outer radius from where the fin is starting, and it extends to R equal to R0. So at any R, we get a top surface, a bottom surface. That's what twice pi r square minus ri square on the top, and on the bottom we get total surface and that is how ds dr we calculate divided by AR, which is cross-sectional area. So governing equation is d2t dr2 plus dA dr by A dt dr H into ds by dr by Ka t minus t infinity, our usual governing equation, that is equal to 0. Now if we substitute our dA dr by A and ds dr by A, we will get d2t dr2 plus 1 by r dt dr. This dx should be dr, sorry, it is dt dr h by k and ds by r by A was found as twice t minus t infinity equal to 0. Please correct this typographical mistake. It is 1 by r dt dr, not dt dx. So please correct it. Now if we substitute theta as t minus t infinity, then theta is basically excess temperature over the ambient temperature. So governing equation will be d2 theta dr2 plus 1 by r d theta dr minus twice h by kt theta equal to 0. I mean, absolutely simple substitution, t by theta. At r equal to Ri, T equal to T0 or T0, which is base temperature, and R equal to Ri, then we can write theta equal to theta naught, and R equal to R0, that is basically outer radius, minus k dt dr equal to h into t minus t infinity. So from the age also we know, if whatever is the age temperature, that temperature minus T infinity into H into area, this area which is at the periphery is the basically that is the thermal energy taken away from the tip, and that is coming in the form of conduction through the material. So at R equal to R naught, minus k d theta dr equal to h into theta. Now we are bringing in a parameter rho, which we are saying beta into r power n, so that d rho dr equal to beta n r to the power n minus 1, and this will be needed d rho dr because we are trying to find out d theta dr, which is d theta d rho into d rho dr. Now d theta d rho is we are fixing as a parameter, and then d rho dr we have found out beta n r to the power n minus 1. So d theta dr we have found out, we have changed the basically independent variable from r to rho. Then d2 theta dr2, again we are writing as d dr of d theta dr. So d dr of whatever we have gotten as d theta dr, we are writing that beta n r power n minus 1 d theta d rho. And obviously, once we differentiate this quantity, that means beta n minus 1 r power n minus 2 d theta d rho, and then d2 theta d rho. Again, when we differentiate that, we get this b square n square r to the power twice n minus 2. So basically d theta d rho, we ddr of d theta d rho, that means again we get this second term. So we d2 theta dr2 we substitute by this quantity d2 theta d rho 2 beta square n square r to the power twice n minus 2. Then we get d theta d rho into all these quantities beta n minus 1 r to the power n minus 2. We had d theta d rho divided by 1 by r, so which is beta n r to the power n minus 2. So basically is 1 by r d theta dr into d theta d rho minus beta n r to the power n minus 2 d theta d rho minus twice h kt into theta. So this becomes our governing equation, which will be reduced to little bit of algebraic arrangement. Beta square n square r power twice n minus 2 d2 theta d rho 2 plus beta n square r power n minus 2 d theta d rho minus twice h by kt into theta equal to 0. We get, we do some further rearrangement of the terms, and finally we get from here beta square r power twice n. If we recall, we substituted actually beta r to the power n as rho. So this gives us rho square d2 theta d rho 2 plus rho d theta d rho minus r square by n square. Again here the two minus signs have come, it is one minus sign actually, minus r square by n square twice h by kt into theta equal to 0. So one minus sign, please be careful, minus r square by n square twice h kt by theta. So this becomes our governing equation. And this governing equation, if this has to make a physical sense, we have to reduce it to divided by rho square and get a form d2 theta d rho 2 plus 1 by rho d theta d rho minus theta, so that it becomes basically our known equation, like Bessel's equation or modified Bessel's equation. It will become modified Bessel's equation. So if this has to be theta, then clearly we can see rho square has to be equated with this term, and that has to make a physical sense. So rho square is r square by n square twice h by kt. That means beta square r to the power twice n is r square by n square twice h by kt. H is the heat transfer coefficient, K is the thermal conductivity of the material, T is the thickness of the fin. These are all physical parameters. Now N, if we substitute N equal to 1, then beta becomes directly function of all these physical parameters. And beta becomes root over twice h by kt. And obviously rho becomes, because rho we took as beta r to the power n, so rho becomes beta r. So therefore we move forward with this understanding that n equal to 1, beta equal to root over twice h by kt, and then rho is basically r square by n square into twice h by kt, where n equal to 1. Then our governing equation matches exactly with the modified Bessel's equation. Now, in our last lecture, we discussed in greater detail about the Bessel's equation and modified Bessel's equation. And modified Bessel's equation of order 0. That means the solutions will be Bessel's function or modified Bessel's function of order 0, first kind, and modified Bessel's function of second kind, order 0. So this is modified Bessel's function of first kind of order 0, and K0 is modified Bessel's function of second kind, order 0. So C1 I naught rho plus C2 K naught rho. Rho is the argument, and basically rho is R dependent function, beta into R, where beta are all physical parameters and R is the radial direction, or the how it is varying with the radius. That is indicated by varying R. So now we can say theta equal to C1 I naught beta R plus C2 K naught beta R. I naught is the modified Bessel's function of the first kind, order 0, and K naught is the modified Bessel's function of second kind, order 0. And we know how we have also in our last lecture studied about some recurrence relationship. We have seen derivative of I naught is I1, and how I naught varies with x with the argument, how I1 varies with x, how K naught varies with x, how K1 varies with x. And I'm just recapitulating our last discussion with tapered fin, where we found their x was the independent variable, and theta we got C1 I naught beta root x plus C2 K naught beta root x. This we just recall what we did with the tapered fin. And x equal to 0, I naught is 1, but K naught tends to infinity. That demands C2 has to be 0. Then we got theta equal to C1 I naught beta root x, and x equal to L, theta is theta naught. So theta naught equal to C1 I naught beta root L, from where C1 is found out. Then the whole solution we found out. But here we have little difficulty, because R is not reaching R equal to 0. We are starting at R equal to R1. So therefore, this derived solution is theta equal to C1 I naught beta R plus C2 K naught beta R. At R equal to R1, we know the boundary condition T equal to T naught, that means theta equal to theta naught. And at R equal to R naught, R equal to Ri, we know the boundary condition, which is T equal to R equal to Ri, T equal to T naught, theta equal to theta naught. And R equal to R naught, we know it is convective boundary condition, minus K d theta dr equal to H into theta. So, because of these two, we are not able to go up to R equal to 0 and apply just the same way we solved for the tapered fin case. Now, what is the way out? I am giving another clue, that is, we are this Bessel's functions and modified Bessel's functions, they can be written in infinite series form, of course, convergent series, but they can be written in integral form also. So, two integral such formulas for modified Bessel's functions are I naught beta r equal to 1 by pi 0 to pi e to the power beta r cos u du, and this is general INBR, and INBR is 1 by pi 0 to pi cos nu exponential beta r cos u du. And when n equal to 0, we get I0 or I0. Similarly, Kn can be expressed as integral formula, and it is basically again cos hyperbolic nu exponential minus beta r cos hyperbolic u du. And for n equal to 0, we get expression for K naught. These are K naught and I naught can also be represented by these two integral formulae. And we are assuming B are greater than 0 everywhere, which is true. And then d I naught br dr is dr of I naught beta r is beta I1 beta r, and ddr of k naught beta r is minus beta k1 beta r. From there, we can write straightforward d theta dr, which is beta c1 I1 beta r minus c2 k1 beta r. That means at r equal to Ri, area, thermal conductivity and gradient minus Ka dt dr, which can be written as minus twice pi Ri into T, that is the area K d theta dr at r equal to Ri. And this is the expression we get. This is basically heat transfer to the fin from the fin base. And this will be entering the fin and will be taken away through convective heat transfer by the surrounding fluid. So we get the solution theta but solution is in terms of C1 and C2. We get heat transfer. Heat transfer is also in terms of C1 and C2. Now these can be evaluated approximately by using different methods for numerical integration or with the help of MATLAB, or the values can be directly obtained from the tables available in this, many books. I have given the reference of these two books. One is Handbook of Mathematical Functions, Formulas, Graphs, and Mathematical Tables. It is famous book of Abramovich, Dover publication, Stegan and Abramovich, and a treatise on theory of basis function. So you can refer to these books and try it out. I would encourage all of you to, I have given all the hints, all the necessary information. I have gone up to the solution also. I have gone up to a heat transfer rate also, but C1 and C2 have not been evaluated. Everything is in terms of C1 and C2. So this is one extended optional assignment also together with this class. Anybody who will be able to solve it and submit on the assignment portal, I will upload this assignment, optional assignment, will get additional marks. If you do not submit, there is no penalty, but if anybody can submit and submit the correct solution, will get additional credit. I will upload this in the assignment section tomorrow. Next class, after this lecture, I have given here a typical example of a practical annular fin. So I said at the outset, it is not one fin. You can see multiple fins, and you can see the tube also. The cross section. So through this tube, hot fluid flows. This heats up the tube wall, and then tube wall heats up the multiple annular fins, and these annular fins promote convective heat transfer to the local ambience in order to cool down the flowing fluid. At times, based on the arrangement, based on the system, the flowing fluid is required to be cooled, or its temperature has to be brought down, or maybe a phase change has to take place through external cooling. So these annular fins provide that enhanced heat transfer or augmented transfer rate. I will stop here today. This is a very important paradigm, and all the clues have been given. Solutions have been done. You have to find out C1 and C2 in a convenient manner and also calculate the heat transfer rate. And problem is similar to tapered fin, only in evaluating the constant C1 and C2, it is not really very straightforward. You have to follow some strategy based on your mathematical knowledge. Thank you very much. Thank you for your interest.